Hello, this is Lab 6, Faraday's Law, Physics 2212. Here's a brief overview. First, we're going to get into the introduction, then we'll look at the physics involved, then take a look at some observations and the code model we used, and then we'll look at the results, and finally get into the key takeaways and answer some questions about the fundamental concepts in this lab. Introduction. Purpose. The purpose of this lab is to observe and simulate a bar magnet falling through a conductive tube, which in our case, that tube being a tube of aluminum foil, in order to show some of Faraday's principles in real life. Results preview. We found that the real model, or I found that the real model averaged at 1.494 seconds, and the simulated model gave us 1.248 seconds. Physics involved. Fundamental principles and equations. We have the Biot-Savart law, or however you say that, Faraday's law, Lenz's law, and Newton's second and third laws in order to create the motion in our glow script code. Observations. Observe model. The initial conditions of our experiment were the foil width being 5 centimeters, the tube length being 46 centimeters, the inner radius being 125 centimeters. Being 1.25 centimeters, the mass of the bar being 23 grams. Our system was the aluminum tube and magnet, and our surroundings were the universe. Observe model. Observations. The magnet moves through the tube very slowly. And for a trial, we found that trial 1, 2, 3, 4, and 5 read 1.5 seconds, 1.52 seconds, 1.48 seconds, 1.44 seconds, 1.53 seconds, respectively. And we calculated an average time between all of these trials to be 1.494 seconds. Here's our glow script model. It's a bit small because of the sheer length of the code for this lab. And this is just adapted from the starter code we were given in Canvas. Glow script code results. So our code modeled the system that we had in the lab and spat out a graph for us showing the velocity of our magnet as it was passing through the tube, and gives our total time required for the magnet to completely pass through the tube, being 1.248 seconds, as stated previously. Results. Our results for this lab were that the predicted and actual timings of the magnets are within error of each other, which shows that the methods behind the code are accurate. Our assumption that no air resistance could have played a role in these slight differences, but honestly that's incredibly unlikely due to the small cross-sectional area of the bar magnet and the low speeds dealt with here. Key takeaways. What if what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The induced current inside of the foil would probably be much greater, increasing the internal magnetic field, preventing the magnet from falling. What if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current would be less, allowing the magnet to fall faster. Thank you.